So I will talk about ENDA-INR experiment. This is a prototype of ENDA cluster. This is will be the introduction for the following reports. So ENDA-INR consists of 16 ENDA detectors located on the open air on the territory of our institute, used to study extensive air showers for energy above 1 PV, testing registration methods and methods for signal processing. Detectors are located on the square grid with a 5 meter step between each other. So other information you can find from this paper. I'm going over. So prototype starts working since September 2021, but in the summer of 2023, the configuration has been changed. Since that time, you can find this distribution of a daily duty cycle. Total duty cycle is about 96%. After deleting unstable periods of area walk and events with noise, we gain this distribution. This is a counting rate of master 3 trigger. It means extensive air shower events with a big total energy deposit. So we have about 100 events per day. And on the right figure, you can see distribution of pulse height spectra for each detector. That indicates about good calibration in experiment. So the registration methodology is the following. On the upper figure, you can see the waveform of typical shower event. The first pulse corresponds to the shower front, and then you can see delayed pulses that connected with neutrons. Pulse shape of neutrons differ from charged component. To select neutron pulses, we use convolutional neural net. More about this method you can find from this paper. The number of background neutrons that can hit our time interval, we count neutrons from 100 microseconds to 5 milliseconds after EOS passage. So the background is 0.5 neutrons per event. For simulation, we use Corsica and fast simulation program that based on Jant4 simulation program. Here you can see the dependence of number of total neutrons versus total energy deposit in event. For simulation for proton and ion and with experimental points, that are in good agreement between each other. So the index in power law dependence is close to 1. For reconstruction, we use a maximum likelihood estimation with the following approximation of lateral density function. We use the following selection criterion. On the right distribution, you can see distribution of shower core error allocation for all selected events, blue curve. This distribution has a long tail because array is very small. But if we use information about neutron component, we can reduce this tail and increase our core resolution. So here, red curve, we select events with a big number of neutrons, more than 4. This is more than our background in event. It's connected, we reduce this tail because high energy hadrons that burn our evaporation neutrons mostly located near the shower core. Here you can see the correlation between reconstructed and true shower size for proton and for ion, respectively. First experimental results is about neutrons time distributions. It can be described as sum of two exponents. The second exponent connected with neutrons that came from large distances. And the first exponent corresponds to the local born neutrons. The parameter in this exponent connected with the neutron lifetime in soil. So it depends on the soil moisture. We simulate three different sets for different soil moistures for dry, for 10% wet soil, and for 20% wet soil. And on the right figure, experimental results, and the most close variant is 10% wet soil. So as we expect, and here you can see the dashed line. This is the estimation of background that we estimate with a special program trigger. And it is very close to other estimation from constant C in neutrons time distributions. And it is also in good agreement with the flux of thermal neutrons on our attitude. This estimation you can find from this paper. Neutron's lateral density function also can be described as sum of two exponents. So this first parameter in first exponent is connected with the characteristic distance between neutrons from parent hadrons. Here you can see a simulation also for proton and for ion with the Kemper fit, a theoretical lateral density function for hadrons in showers. And on the right figure, comparison with the experiment and the simulation with background without any normalization. So the results are also in good agreement between each other. And we also compare the results with the experiment Prisma 32 that were consisting of 32 ENDA detectors located in MIFI in complex Nevat. But arrays have different external conditions. Prisma located in the building, and we have effect of neutron scattering from walls and roof, and the second parameter will be another. So it's different, but the first parameter are in quite good agreement between their measurements. So that's all. I go to conclusions. So ENDA-INR works in stable mode. So we obtain the following distributions and dependencies, and they are in good agreement with our simulation results and with the results that previously obtained at this Prisma 32 experiment. Thanks for